One extremely nice property of the elementary matrices is that they're all invertible, and not only are they invertible, their inverses are actually pretty easy to find. So let's figure out the inverse matrix for this row operation. So the row operation that interchanges, say, row 2 by row 4 in a 4 by 4 matrix. So here is that elementary matrix. You can see it's the 4 by 4 identity, but I've just swapped row 2 and row 4. But what is the row operation that would undo this? Well, the row operation that would undo interchanging row 2 and row 4 is just switching them back, right? If you switch row 2 and row 4, if you switch them again, then you're back where you started. So the matrix the inverse for this matrix should be the elementary matrix for the opposite row operation. But by opposite, I mean sort of inverse, which is actually the same row operation in this particular case. So that means that the inverse matrix for this elementary matrix should actually be the same thing. So 1 here, and then 1's like that, and 0's everywhere else. Just to check, let's actually work out this product and check that we get the 4 by 4 identity. So first row times first column gives us 1, 0, 0, 0, so just 1. And then as we sweep the first column down, we get nothing but zeros. And then take the second column here, sweep it down. You get 0, 1, 0, 0. And then take the third column, and you get 0, 0, 1, 0. And then last column, 0, 0, 0, 1. And that is the 4 by 4 identity matrix. So the elementary matrices that swap rows, those are actually their own inverse matrices. All right, well now let's look at the elementary matrix that multiplies a row by a scalar. Here I have a 3 by 3 example, and so I should have a -4 here. So here's the matrix that multiplies row 3 by the scalar -4. What would the opposite row operation be? What row operation would undo this row operation? Well, that would be multiplying row 3 by, right, we need to undo multiplying by -4. And to undo multiplying by -4, you should multiply by -1/4. So this matrix for the inverse of our elementary matrix, it should just embody the row operation multiplying row 3 by -1/4. And that would be 1, 1, -1/4, like this. Oops, -1/4. There we go. And we can check. We can actually do this matrix multiplication and see if it works. And it does. You know, we get 1, 0, 0, 0, 1, 0, and then 0, 0. And then for this bottom right corner position, that's when we get -1/4 times -4, and that's 1. Okay, so if we have one of these elementary matrices that multiplies a row by a scalar, the inverse of that is, well, it just has 1's down the diagonal, but in whatever position where we had the scalar, we get the reciprocal of that scalar instead. Right? So this is another elementary matrix of the same type. Okay, for the last type of elementary matrices, those are the elementary matrices that add a multiple of one row to another. So here is the 4 by 4 matrix that adds 2 times row 1 to row 4, right? That's what this 2 down here is doing. So what would the opposite, or what row operation would undo this? Well, if we added 2 times row 1 to row 4, then I guess what we should, to undo that, we should take row 4 and subtract 2 times row 1. Right? That would undo this row operation. So what is the matrix that embodies this row operation? Well, it's 1 down the diagonal, and then instead of adding 2 times row 1, we should subtract 2 times row 1, so from row 4, like that. So let's check that this does give us the identity matrix. So going down the first column here and first row there. So 1, 0, 0, 1, 0, 0. And then when the first column hits the last row, we get 1 times minus 2 plus 2 times 1. So that all cancels and we get 0. For the next two columns, don't really do anything interesting. They just sort of pick up the ones in the middle here. So 0, 1, 0, 0, and 0, 0, 1, 0. And then for the last column, when we sweep that down, right, this minus 2 hits that 0, and so we just get 1 times 1 in this last position here. So like that. And so it worked. Right? This is the inverse, this elementary matrix on the left is the inverse of the elementary matrix on the right. So in general, if we have one of these elementary matrices that has adds one row, a multiple of one row to another like this, the inverse of that matrix is still ones that down the diagonal, but in the same position wherever there was a scalar, instead it's the negative of the scalar. And that's the inverse matrix. And this, again, is an elementary matrix. So all of the elementary matrices actually have inverses that are other elementary matrices.